This is another equilibrium and moments question from this particular past paper from CCEA. So this one's from June 2019. It's obviously the applied paper, and this then is question 5. It says a uniform ladder AB of mass m1 kilograms and length 6 meters rests A on a rough horizontal ground. The ladder is inclined at theta to the horizontal where sine theta is 12/13. I hope you recognise the 12 and 13 there. The other end B rests against a smooth vertical wall. When John stands on the ladder at a distance of x meters from A, the ladder is on the point of slipping. John has a mass of m2. If mu is the coefficient of friction between the ladder and the plane, show that the distance John is from A equals this. So quite a messy looking equation there. So first of all, we need a diagram to work out what's going on. So here is our wall and our ground, and we have that, and that's going to be our theta. It is a uniform ladder, so we have an m1g acting that way, and we reckon John, let's put John here, m2g acting that way. So what else are we going to have? We're going to have an r here, which is our normal reaction, and then here is going to be our friction, so that's going to be mu r. Again, mu gets a mention there. The other force we have acting on this one is going to be the normal reaction with the ladder up against the wall, so I'm going to call this one S. My S's tend to look very like 5, so I'm going to try not to let that happen. So that's what we have. I'm trying to think if there's anything else we need there. I think we're good. The other thing worth a mention is we know that sine theta is 12/13. Sorry to turn this the other way around on you there, but that's 12, that's 13. With a bit of Pythagoras, that's 5, and that means that cos theta is then going to be 5/13, and that might be quite useful for us at one stage. Generally with these questions we're going to do 3 things you always do. Everything going up equals everything going down, and everything going left equals everything going right. So resolving up and down first of all, and then take moments about somewhere, is going to be r equals m1g plus m2g. Going this way here, we're going to have then S equals mu r, and so you can already kind of substitute this in. It kind of might make our life easier at some stage. So my S then is mu upon m1g plus m2g. Notice there's like a common g, so you haven't even been able to see that, sorry. So S is mu r, everything goes left equals everything going right, and then my r I know is this, so I substitute here, so we could then rewrite it as mu g m1 plus m2. So we're going to take moments then about the foot of the ladder, and this is kind of ends up being messy enough, but let's see how we get on. So if I want to call this A, and we'll call that, sorry, it tells you that anyway, B. So I'm going to take my moments then about A and see if we're able to see what we're doing here. So moments about A clockwise equals anti-clockwise, and let's see then what we have. And we have distances in here as well that we need to work out. We're told the ladder then is 6 long, so we have that. So let's get a shorter pencil here, we can see actually what we're doing. The reason taken by A is then the mu r and the r have no effect, and then the m1g, that takes it anti-clockwise, that takes it anti-clockwise, and that takes it clockwise. So we just need to try and work these out. So the clockwise one is going to be 6 times S, that's theta, which means that's theta. Remember by your kind of third form geometry, and we're trying to resolve it perpendicular, so that would be 6 times S, and that's going to be then sine theta. So 6 times S sine theta is that one there. This one here is going to be 3 times m1g. That is theta, so that would be 90 minus theta, And that there then is theta. You can do that a couple of different ways. You can pick numbers for it. Sometimes it helps people. There's a wee kind of right angle triangle there. I hope you can see that. Say that's 60. That's 30. And because I'm doing the perpendicular of 30, that's 60 again. So that's theta. So we're going to cross the theta. So that's going to be cos theta. And that's our distance x, which we're trying to work out. And that's m2g. And because of exactly the same rule, that's going to be cos theta then as well. So my s, I know, is this. So I'm going to substitute it in as well, and I'm going to change my sine theta for a 12 over 13, and I'm going to change my cos theta for a 5 over 13 as well, and see if we can kind of get things tidied up. So go on to the next page. Oh, it's on the other side, that's quite frustrating. Okay, so we're going to go sine theta, which is 12 over 13. So we're going to have 6 times 12. So it's going to be 72 over 13 times by this. That's a 6 sine theta. And then what did I have? Mu g m1 plus m2. m1g times 5 over 13. Plus x m2g times 5 over 13. So how can things tidy up? 3 terms, there's a g in all of them. So that goes. Also, I'm going to times 3 then by 13. So I'm going to be 72 mu m1 plus m2. 3 times 5 m1, so it's 15 m1 equals 5x m2. I think we're pretty close to having what they need. So we're trying to get the x on its own, that's what we have. I'm going to take this, why do I have 2 equal signs? That's a plus there, apologies. So we take this over the other side, so 72 mu m1 plus m2 minus 15 m1 equals 5x m2, and dividing then by 5m2 I think gives us what we're looking for. 72 mu m1 plus m2 minus 15 m1 all over 5m2, and hopefully that's what they want. Yeah, that looks just all of it.